This video I would like to help you understand relative motion and Galilean transformation of velocity. So what I want to show you here is a little animation that I made where you're going to see the truck with a flatbed and a person standing on the truck, which is going to move to the right with a constant velocity. The person on the flatbed is going to throw a ball forward. So let's see. I have drawn a few puffs of dust at the beginning to help us determine the velocity with respect to different systems of reference. So the first thing that I want you to notice is the velocity of the ball with respect to system S prime. System S prime is the system of reference that is attached to the truck. System of reference S, is the system of reference attached to the observer on the side of the road, which does not move with respect to the ground. So in this problem we have two systems of reference, S prime and S, and an object that is moving. So first let's focus on the velocity of the ball, the object, with respect to S prime. I'm going to move the movie frame by frame so we can make a measurement of that. Let's assume that in this animation every square represents 1 meter and that the time difference between frames is 1 second. Of course, that means that the person standing on the truck is about 6 meters tall, but never mind. So let's move this movie frame by frame, as I said. And here in this frame we see that the ball is already 1 meter away from the y prime axis, the y axis of system S prime. In the next frame, 1 second later, we can see that the ball is now 2 meters away from y prime axis. Next frame, 3 meters away. Next frame, 4 meters away. Next frame, 5 meters away from the y-axis of S prime, and so on. So we can tell already that the ball is moving with constant velocity in the x direction and that velocity is 1 meter per second. Now let's go back to the beginning of the animation. Please ignore the vectors, we'll talk about that later. And let's focus on the velocity of the ball with respect to the observer standing on the side of the road. So at this instant of time, the ball is 1, 2, 3, 4, 5, 6 meters away from the y-axis of system S, 6 meters away. In the next frame, we can see that it is now 9 meters away. And since I put a little puff of dust there, we can tell that the difference in position between one frame and the next is 1, 2, 3 squares, which I said was 3 meters. So every second, the ball is moving 3 meters away from the y-axis of system S. So the ball, with respect to system S, has a velocity of 3 meters per second. The velocity of the ball with respect to system S prime, as we measured before, is 1 meter per second. So observer S prime measures the velocity of the ball as being smaller than the velocity that observer S measures. Now what accounts for this difference? What is behind the difference in the velocity as measured by these two different observers? Well, notice that system S prime is moving with respect to S. That is, the truck is moving with respect to S. If the truck had not been moving, observers S prime and S would have coincided on their measurement of the velocity of the ball. But when the truck is moving, they will not coincide. Those measurements of the velocity would not be the same. As we said, S prime measures in this animation 1 meter per second, S measures 3 meters per second. And the connection between those two measurements is through the velocity of the truck with respect to S. Let's measure that velocity. Watch the y-axis, the red y-axis, in this frame and in the following. It moved 2 meters forward. In every frame is moving 2 meters forward. So that means that the velocity of the truck with respect to S is 2 meters per second. So now we have three measurements of the velocity in this animation, in this problem with relative motion. One is the velocity of the ball with respect to s prime, that is 1 meter per second. Another velocity is the velocity of s prime with respect to s, that was 2 meters per second. And the final velocity is the velocity of the ball with respect to s, which we measure it to be 3 meters per second. So let's derive an equation that relates these velocities. That equation is called Galilean transformation of velocity. And to do that, I'm going to show you, we're going to draw vectors at different locations and see what we obtain. Let's start by drawing the position vectors for the ball as measured with respect to s prime and s, and for s prime with respect to s. So the first one, the blue position vector, ROS1, denotes the location of the ball as measured by observer S. The ball is, we're going to call that the object, so that's O stands for object, and the 1 on top of the vector means that this is time frame number 1, which we chose arbitrarily. The yellow vector that you can see there is the position vector for the ball as measured by observer s prime, that is vector ROS prime for time frame 1. Finally, the green vector is the vector that tells us the position of the system of reference s prime with respect to s. In this next frame, we also have drawn the same location vectors, position vectors, but for a different time frame. A certain amount of time delta t has passed between those two frames, which I'm going to draw here together, time frame number 1 and time frame number 2. Now we're going to redraw the position vector ROS prime 1 so that it starts at the origin of s prime at the second time frame. Remember, we can always redraw a vector provided we don't change its magnitude or its direction. We're going to need this vector because with ROS prime 1 and ROS prime 2, we're going to be able to find what's the displacement vector of the ball as measured by the observer on the flatbed of the truck. This observer measures the ball as changing its position from 1 to 2, and that change in position is given by the vector delta ROS prime as indicated. This vector is important because it is related to the velocity of the ball with respect to s prime. So let's find other displacement vectors. The displacement vector of the ball as measured with respect to system S. To do that, we simply draw a vector that starts at the head of ROS1 and ends at the head of ROS2. This represents the displacement of the ball between those two time frames as measured by the observer at S. As we mentioned before, that displacement is going to be bigger than the displacement of the ball as measured in system S prime. The difference between those two vectors, we can see that is this green vector underneath, which you can check easily that it is the same as this vector that goes from the origin of S prime at time frame 1 to the origin of S prime at time frame 2. So that is the vector displacement for system S prime as measured by S. So the connection between those three displacements then can be written in an equation, in a simple equation, that tells us that the displacement delta ROS should be equal to the displacement delta ROS prime plus the displacement delta R S prime S. If you divide these displacements by the amount of time that it took, the amount of time between those time frames, then you will get that the velocities are related in the following way. The velocity of the ball with respect to S is equal to the velocity of the ball with respect to S prime plus the velocity of S prime with respect to S. This simple equation that relates the velocity of an object as measured in two different systems of reference is called the Galilean transformation for velocity. And I will show you in the next video a few examples of how to use this equation